Now we're going to look at a very famous algorithm called the Gram-Schmidt algorithm. The name stands for two mathematicians, Gram and Schmidt. So we'll take a look at it, and it has to do with linear independence, and in fact, it is an algorithm. I mean, for right now, its main purpose is to detect whether a set of vectors is linearly dependent or linearly independent. We're actually going to see later that it is enormously useful in a lot of practical applications, but that's not going to come up for a while. So right now it is, again, I'm sorry, just kind of weird and abstract. I should also say another thing about it. We described one algorithm already. That's the k-means algorithm, and now we're going to describe Gram-Schmidt. I guess I'm not one who thinks that students should be forced to implement these things by themselves. I mean, I don't know. I mean, I suppose there's a point to it. I don't, but it will describe it. And of course, when you're doing this in practice, you're going to rely on implementations written by others. So the point of it is not that you're going to go out and code this yourself. The point is you should understand what it is and how it works and what it does. But when you actually use it, you're going to call some routine written by someone else. Okay. So here's what it is. For now, we'll see that it's a lot more than this, but for now, here's what it is. It is simply an algorithm that checks if a set of vectors is linearly independent. That's it. We're going to see it has a lot of other uses later. In fact, in the whole class, there's about 2 or 3 algorithms, and they're basically all related to it's all this one. It's just Gram-Schmidt. Okay, so here it is. We're just going to jump right in. And like I said, right now it's kind of abstract, but that it'll emerge later in the book that it has a lot of uses. Okay, so we're given a set of vectors, and they're n vectors, and we have k of them. And what it's going to do is it's going to process the vectors one at a time. And in the end, it is going to we'll be able to use this to determine if those vectors are linearly independent or linearly dependent, right? To remind you, linearly dependent means that there's a linear combination of them that's 0, with the coefficients not all being 0. Linear independent means that's not the case. Okay, so here's what it does. The first step is it takes the ith vector, ai, and it subtracts from ai it maintains a set of vectors, q1, q2, q3, up to qk, unless the algorithm terminates early. It generates a set of q's which are orthonormal. I should mention that the notation q this is just a convention. Typically, a set of q's are orthonormal vectors, right? By the way, same for u's and v's, and it is just convention. So okay, but in this case, it's following the convention. So the vectors, it's going to generate a set of vectors q1, q2, which are orthonormal. So here's what's going to happen. You're going to take ai, and you are going to subtract from it the inner product of q1 and ai. Well, that's a number times q1 and so on. Now, what you'll recognize, you may remember this from last time, in fact, is that if ai is a linear combination of q1 up to qi minus 1, then in fact, all of this is equal to ai, and qi tilde is 0. So if qi tilde turns out to be 0, that means that ai is a linear combination of q1 up to qa minus 1. Q sub I minus 1, sorry. Now what we do is, again, we check if qi tilde is 0. If it is, we quit. And because in that case, it'll turn out that these vectors are linearly dependent. If not, if it's non-zero, we simply divide by the norm and we normalize, and we get qi from qi tilde. Okay, so if this algorithm runs all the way to the end and does not quit, as in step 2 here of the algorithm, then that's going to tell us that those vectors are linearly independent. If it stops in algorithm in step j, then it's going to tell us that vector aj is actually a linear combination of the previous ones, a1 up to aj minus 1. And that means that our set of vectors is linearly dependent. Okay, so that's the algorithm. Now, the one that's actually used numerically in practice is mathematically equivalent, but it's not quite the same as this. I mean, it generates exactly the same vectors and things like that, but it's slightly different. Okay, so let's walk through an example. Here's two vectors, which are two vectors. They're A1 and A2. This gray circle is showing you all points of norm 1. So it's a circle, basically, of radius 1. Okay, and so let's see. So that would tell us, for example, the norm of A1 is about 1.3. I'm making that up, but that's about it. Okay, so let's run Gram-Schmidt. Well, we grab A1, and the first thing we do is we subtract off from A1 a sublinear combination of the previous Qs. But we have no previous Qs, so we subtract nothing. And so that tells us that Q1, this is the first step, right? Q1, there we go, sorry about that. So Q1 tilde is in fact just nothing but A1. Okay, so now that's the first step. We check if it's 0. It is definitely not 0. And so we normalize it. And that means we shrink it to get Q1. And you see now it's green. And you can see that its arrow, the tip of the arrow, is on that unit circle. That's what it's called. And that means it now has norm 1. So that's Q1. Okay, next step. Now it gets interesting, right? Because now we go over to here. And what happens is we take A2 and we subtract off from A2 a multiple of Q1 to make the result orthogonal to Q1. And so the correct thing to subtract is minus Q1 transpose A2, Q1, and that's this vector here. And we end up with this red vector here, which is Q2 tilde. Now notice that Q2 tilde is orthogonal to Q1, because that's actually what we're doing, is we're slowly producing, and we're generating a set of orthonormal vectors. Okay. Now, at this point, they're just ortho. They're not normal yet. And so what we do here is we check if Q2 tilde is 0. It is not 0. And therefore, we scale it to make it have length 1. And we end up with, there we go. There's Q1 and Q2. And so this is extremely boring. There's no reason to have any interest in it, because there's nothing, just to be completely open about it, there's nothing practical we can do with this yet. So I'm admitting it. Okay. So the point is, if you run if you run Gram-Schmidt on these two vectors, A1 and A2, that's what comes out, Q1 and Q2. And you could well ask, who cares? And I would say you don't know. The answer is you don't know yet. You'll know later that this actually can do all sorts of super cool practical stuff. But for the moment, this is all just weird and abstract, whatever. So just trust me. All right. So we can analyze this a bit. I'm not going to go into it in too much detail, because this is the kind of thing that's best done by you kind of, reading through the book carefully and stuff like that. But I will say just a few things about how the algorithm, what it does. So the first thing, and I think our example already kind of gave us a hint, is the Qs that come out of the Gram-Schmidt algorithm are orthonormal. Okay? And the reason we can check, suppose it's true for I minus 1, and we'll show this by recursion. Okay? In that orthogonalization step, you are actually subtracting exactly the coefficient you need to of the previous Qs to make it orthogonal to all of them. Okay, so when you finish, Qi tilde is orthogonal to all the previous ones. That's how that works. Now to see that, all we do is we take an inner product with Qj. So Qj transpose Qi tilde is equal to, and this is Qi tilde here, and I'm just going to simply work it out and see what we get. But over here, we get things like Qj tilde Q1. Well, that is going to be, that's going to be 0, right? So the only one that comes out is we end up with Qj transpose, the inner product of Qj and Ai, and then again, Qj and Ai, and you subtract them, you get 0. So it's orthogonal. And what that says is that it says Qi tilde is orthogonal to all the previous ones, but if I scale it by a number, because to make its norm 1, it's still orthogonal. So the Qs are orthogonal. And of course, the normalization step guarantees that the norm is 1. Okay, so it says that the Qis that come out of the back end of the Gram-Schmidt algorithm are orthonormal. Okay. Now, if if the algorithm has not terminated before iteration I, then it turns out AI is a linear combination of Q1 through QI. And we can even see that because we can actually very explicitly write down what the linear combination is. It is literally the norm of QI tilde times QI plus, and then again, this inner product. These are inner product coefficients. It's the one you've already seen before in an orthonormal basis expansion. So what we do is we get that. That's very explicit. So AI is literally a linear combination of Q1 up to QI. Okay. In fact, well, that's one of the ways we could say it is that each AI is a linear combination of Q1 up to QI. Okay. And it turns out the reverse is true too. Each QI is a linear combination of A1 through AI. And again, you can see that by induction. I'm not going to go into the details there, but that's how that's the case. Okay, we get to early termination. If it terminates in step J, what that says is that QJ tilde is equal to 0. That means that when you took AI and AJ, and when you subtracted the appropriate linear combination of Q1 up to QJ minus 1 from it, you got 0. And that tells you actually that equality holds. Now we'll notice that each of these QIs here is a linear combination of the AIs, A1 up to AJ minus 1. So this is a linear combination of linear combinations. Linear combination of linear combination is again a linear combination, and that says that when it stops, it says that AJ is a linear combination of A1 up to AJ minus 1. That is one of the definitions of being dependent. So what that says is that the Graham-Schmidt algorithm, if it terminates early, then it terminates because the A's you started with were linearly dependent. I want to say a little bit about the complexity of the Graham-Schmidt algorithm, about how long does it take to, basically how many flops does it take to actually carry this out. Well, let's figure it out. In iteration I, you have to evaluate I minus 1 inner products, right? And that costs, each inner product costs 2n minus 1 flops. And there's I minus 1, so that's that. Okay, so that's the total number of flops. To compute QI tilde, you have to subtract off various things, and that costs you 2n I minus 1 flops. Okay? Then it costs you 3n flops to calculate the norm and then divide QI tilde by that norm to get QI. So that's 3n flops. And the total is now, we add this plus that, and we have to now sum that from I equals 1 to k, and you get something horrible that looks like that. Now, you could work out what that is. In fact, it's exactly this, and I'll tell you why. I'm going to use a formula, which you can just remember or look up or go to Wikipedia to find out or something like that. And it's this. It's the sum from I equals 1 to k of I minus 1 is actually k times k minus 1 over 2. In other words, the following sum, if you can check it if k equals 5, and this says you should add up 0 plus 1 plus 2 plus 3 plus 4. And you will find out that that is 5 times 4 divided by 2, which is 10. And it's correct. I mean, maybe I misspoke it, but it's correct. So anyway, so you get some horrible thing like this. Now, what you have to remember about flop counts is it's extremely crude. So we're going to drop what we call non-dominant terms, right? So for example, when you work this out, the biggest term you're possibly going to get is going to be this 4n times the k squared divided by 2. That's 2nk squared. All the other terms have a coefficient of either n or k, which is smaller. And we're interested in the case when n and k are reasonably large, so we just drop them. And so this is completely standard in a flop count. And you would say that Graham-Schmidt has a complexity of 2nk squared flops. And the truth is that it's not quite right. But the whole flop count model is so approximate that this is just fine, right? Because we're pretending that multiplies and adds and divisions and things like that, even a square root, because we have to calculate a norm, and we're kind of pretending that these all cost the same, which they don't. Okay, So you get 2nk squared. That's interesting, right? Because it tells you that it is quadratic in the number of vectors that you apply it to, and it's linear, you would say, in the dimension n.